Okay, hello. You should be able to see my slides, and hopefully you can hear me talk. If you do, give me a thumbs up so I know that this stream is coming through. Okay, thank you. Thank you, Nimat, and everyone else. I'm not going to read all your names. Okay, so today we're going to talk about stress, strain, and Young's modulus, and bulk modulus, and shear modulus. Before then, on Wednesday, we're going to talk about gravitation. And so I got one question, well, two things. So yes, we're continuing the class through next Wednesday, not next Monday, as I said earlier. And about chapter 13, so what we're going to cover is just the parts up to 13.5. So when it says in the syllabus that it says 13.5, I think that is supposed to refer to the fact that we're covering until 13.5 rather than only 13.5. So I don't have the syllabus right here with me, so I can't quite check. But okay. So we're going to talk about stress, strain, and Young's modulus today, and so we're going to want to define those terms. And so what we're going to let's start with getting my slides in order here. Okay. So we're going to talk about stress and strain, and so we're going to have to define what stress and strain are going to be. So let's introduce. Let's see, testing. Yep. So we're going to introduce stress and strain, which are specific definitions of things in physics, much like force or torque. And in this case, let's start with stress. So stress is going to be the force per unit area. So, and there's different kind of stresses that we can apply to an object. We can have tensile stress. So that's when if we have an object, we apply a force over that the cross-sectional area. There's a cross-sectional area A, and we pull on both sides on this object, and there will be a tensile stress on this object. Similarly, if we push on both sides of this object with a cross-sectional area A, if we push on this side and push on that side with a force F, there will be a compressive stress on that object. There's also volume stresses, which are stresses that apply to all sides of the object equally. So if there's a pressure, then I should say volume stress here and introduce pressure when I introduce it later. But if there's a force on all sides of this cube, then there will be a volume stress on that object. Now finally, there's the stranger one. That's the shear stress. That's if we have an object that let's see, you gotta make sure I draw this correctly here. So if we have an object that deforms from its original shape because of some force that is applied in the opposite direction as where we measure the cross-sectional area. So this is the textbook uses as the example a bookcase. You all know that if you buy one of those IKEA bookcases and you don't put on the cardboard on the back, then you can just push on the side and it will just completely collapse. So then you're applying a shear stress to this bookcase, and it just collapses under the influence of that shear stress. So these are a couple of different types of stresses. So tensile, compressive, which are the opposites to each other, and then volume stress, which is in 3 dimensions from all directions, and then shear stress, where the force is in the opposite direction as where we measure the area. In all the other ones, we'll measure the area in the same in the direction perpendicular to the force. So if stress is a quantity that's force per unit area, so it's force over area, then the units of stress will be, and there's no real symbol for stress in general, so I'm just going to write stress here. So the units will be in newtons per meter squared, or that's a unit that we also call the Pascal. So PA for Pascal, the name of the French mathematician who I guess is now associated with that. This is the same unit as we use for pressure, and we'll actually come back to that when we talk about volume stress, which is better expressed in terms of that pressure. So all of the other units of pressure might also apply here, but Pascal is the one that is the SI unit. So this stress, whether it's tensile or compressive, volume stress or shear stress, I mean, we immediately see in shear stress we've already introduced a deformation here, but the stress will cause a deformation of the object, or can cause a deformation of the object. So stress causes strain. That's the deformation of the object. So, and it's not just the deformation, the strain is actually the fractional deformation of the object. So that's going to be the change in length over the original length in general. So if the deformation is let's say, if we pull on something in a tensile stress scenario, if we pull on something and it becomes 1% longer, so delta L is 0.01 times L0, then the stress, the strain caused by that stress will be 0.01 or 1%. So the strain has units that are dimensionless. So it's a dimensionless quantity, whereas the stress itself is in units of Pascal. So now I already indicated that the stress causes strain, causes deformation, and of course there will be a connection between the two, and that's what we're going to talk about in this chapter. So the stress will be equal to the elastic modulus times the strain. So if there is a certain stress applied, then we will get a certain strain. So think of this as, this is similar to F equals ma in the sense that it is written incorrectly, and it would have been probably more causally correct to write that the strain, which is the effect, is the stress over the elastic modulus. Now from this first equation we can see what the units of this elastic modulus have to be. So they're going to be units of stress over units of strain. So that's units of stress over units of strain. So that's Pascal over 1, or just Pascal. So the elastic modulus will be in units of Pascal, just like the units of stress. And so essentially it will allow us to go from the stress applied to the strain by dividing, if we have our stress in units of Pascal, then this will be in units of Pascal. And we end up with the dimensionless quantity for strain, which we want, which we could turn into a percent if we wanted to. Okay. So now let's look at that in these couple of different cases that we identified here for the different types of stress: tensile, compressive stresses. Those are the two that we're going to treat in the same breath, and then we're going to introduce volume stress and shear stress. So let's start with compressive and tensile stress and strain. So that's the first type. So in this case, and actually I can show that on the slides, So in this case, we have a force that is either pulling on the object that has initially a length L0 and that becomes longer by a length delta L, or we press down on the object and it decreases in length by a length by an amount delta L. So the original length L0 becomes L0 minus delta L. The cross-sectional area of this object is going to be A. That's what allows us to take that force and turn it into a stress by dividing by the cross-sectional area. So the stress will be equal to the force, which is applied perpendicular to the surface area. So it's F over A. And the stress, the strain is going to be delta L over L0. And they're connected through this elastic modulus, which in the case of compressive and tensile stress and strain is written as Y. So the elastic modulus is Y, and this is called the Young's modulus for a material. And so the stress F perpendicular over A will be Y times the strain, delta L over L0, or Y, if you were to make a measurement where you apply a certain set of forces, so F times L0 over A times delta L. So a larger Y will mean that you need a larger force over the same cross-sectional area to obtain the same strain, to obtain the same change in length of the material. So a larger Y corresponds to something that is more difficult to deform. So we can apply this to an example. So if we have, this is I think one of the examples in the textbook. If we have a metal, a stainless steel rod that is hanging from the ceiling, and it has a Young's modulus, which will be in units of Pascal, and it's going to be 2 times 10 to the 11th Pascal. So what you'll see is that for things that are difficult to deform, these Young's modulus values are going to be very large. So 10 to the 11th Pascal means that the deformation of 10% of the length will require 1/10 of that Young's modulus in force over unit area. So let's say the length here is 2 meters, and let's say this cross-sectional area is 0.30 centimeters squared. Let's say there's a mass attached here where the mass is 550 kilograms. Those are the numbers that the textbook uses. So what is the delta L for this steel rod? So these are not very complicated problems. There's not a whole lot of conceptual thinking here. The only thing you have to do is take the numbers and plug them into the equation. The part where it becomes more difficult is when we introduce strain, when we introduce shear stress and strain, because that's when you have to actually think about what cross-sectional area are we talking about, what length do we need to include, but we'll get to that in a minute. So the force here will be M times G, and we're going to ignore the mass of the rod. If you calculate the mass of the rod, you'll see that it's much smaller than the mass of the 550 kilograms here, so we can ignore that. So we can calculate the stress. The stress will be F perpendicular over the cross-sectional area in Pascal. This is going to be 1.8 you plug in the numbers, times 10 to the 8 Pascal. And we can calculate the strain from this stress. So the strain, delta L over L0, will be, we got to invert our equation here. So 1 over y times the stress, F perpendicular over A. And that will give us then that delta L is 1.8 millimeters. So you can plug in the numbers if we take the 1.8 here and divide by, wait, how does, let's see, maybe I'm just looking at those numbers and they don't seem to make sense really. So so let me just double check that I don't have a typo in here. Right. No, okay, they do make sense. Yeah. So delta L will be so yeah, so the numbers do make sense, sorry. So over the 2 meter length, the change due to this mass will be an extension, because this is a tensile stress. This is tensile stress. So the strain will be an extension of the original length. So that extension will be about 2 millimeters. So it's about 1,000th of the original length. And that's typical for the magnitude of these strains. We don't see strains that are on the order of 10%, except if you go to things like rubber bands and so on. But then it's probably better to not model this with an elastic modulus, but then you're probably better off modeling it with a different system, because the assumptions of this elastic modulus wouldn't be satisfied there. Notice, by the way, that this is very similar to our spring equation, right? Where we had F is K times delta X, Hooke's law. Except now we have F is Y times delta L with some other constants thrown in. So we could actually calculate what K has to be. And K will have to be Y A over L0. If we use that K, then F perpendicular will be K times delta L. So what we're doing here is essentially treating this system as a spring, except a spring with a very high spring constant, which means it is not very springy, right? It's not easy to deform this object. And this is, of course, something that we can apply in many different cases, right? And obviously, one of the things we can also do is look at this equation and now say, well, if we wanted this rod to not change its length by 2 millimeters, how would we avoid that? Well, one of the things we can do is decrease or increase the cross-sectional area. If we increase the cross-sectional area, what happens? If we increase the cross-sectional area for the same force, for the same mass and force that is applied, we'll now get a smaller stress. If we get a smaller stress, that will give us a smaller strain. So an increased cross-sectional area gives us a smaller deformation. And that kind of makes sense, because you spread the force over a larger cross-sectional area, and so to some extent you give the object more strength to withstand that deformation. And that's something that is exploited, of course, in let's see, let's come back to that in a minute here. Well, actually, let's go through this first. So in some cases where we do have, in this example, we have a mass on both sides of this rod, and so there's actually going to be a tensile stress at the top where the object is being pulled at on both sides, and so it's going to extend in length, which is why this top part here looks longer. At the bottom, there's actually compression, there's pressure inwards, and that is going to cause this this rod to be shorter at the bottom, and so that causes this this deformation of this rod. So that's also what is used in I-beams in construction. So so this gets back now to increasing the cross-sectional area. So if we look at these I-beams, what we're trying to do when we use I-beams is prevent bending. So instead of using a rectangular rod, what we're using is a rod that looks like this. In fact, it is probably more correct to start from, or it makes more sense pedagogically, to start from a rod that looks like this, just the inner part here, and then we add those flanges to it. Why would we add those flanges? Well, that's to increase the cross-sectional area here and decrease the deformation of this beam. So if you think of this as an I-beam that is attached to the wall here, let's try to draw this. So we have an I-beam like this, and the other flange is there. Not doing a very good drawing in here. Not doing a very good job drawing. So so what happens is that if there's some force that is applying downwards on this I-beam, it will cause a tensile stress in the top flange of the I-beam, and it will cause a compressive stress in the bottom part of this I-beam. And by increasing the surface area A, we can actually decrease the deformation, and we can decrease how much this I-beam will bend. Also, one of the things we can do, and what we sometimes do in physics, is we'll just consider only this half of the I-beam as a system, and then look at what force is operating on that I-beam here. So it's a tensile force on the outer part of the I-beam. The tensile force will be in this direction, so that's our F perpendicular. At the bottom part, the tensile force, the compressive force, will be in this direction, so that's going to be my F perpendicular. And I'm going to make this F1, and this is F2. And so those F1 and F2, going back to what we talked about last week, those will build a torque that counteracts the torque of this force around some pivot point, which we could pick, of course, anywhere, and that will make sure that this I-beam remains in static equilibrium. This is exactly the same scenario with the force pulling towards the wall at the top and the force pulling away from the wall at the bottom, as we looked at last time with the door, right? Remember that we solved this problem, and we had the force at the hinge that is pulling the door towards the wall at the top, and is pushing the door away from the wall at the bottom. So that's the same thing that's happening here in this I-beam, and here we're now increasing the surface area A to decrease the deformation. And so that's one of the reasons why we use these I-beams. And of course, you need the central webbing to make sure that those I-beams don't separate. That's the reason for that part. Okay, so that's compressive and tensile stresses. And one of the examples in the textbook, well, there's a couple of different problems, but one of the problems that you'll find, I think it's in the maybe in the challenge problems or maybe in the extra problem section, but it combines all of this static equilibrium with stresses by asking you to calculate how much a light pole or a utility pole gets shorter because of all of the forces that are working on this utility pole. And in particular, it's a utility pole that is at some corner. So these are both horizontal wires and tensions that connects the cables from one street to the perpendicular street. And then there's what is called a guy wire, which is connected to the ground here to prevent this pole from just toppling over in that direction, right? So the problem here is really a three-dimensional problem, because we've got a force here in the x direction, a force in the y direction. If this is the z direction in the top, towards the top, vertically upward, then this force will be in the towards the ground, but it will also have some components in the x and the y direction. So that's an interesting problem to look at if you want to put everything from chapter 12 together in a single problem. Okay, and that will be a problem on, of course, compression, because ultimately the force at the top of this utility pole will be downwards, so the utility pole will decrease in height just a tiny little bit, depending, of course, on the Young's modulus of that utility pole. So one question I got is, why is the force perpendicular? So, or why do we write that this force is perpendicular? It's because it's perpendicular to the direction in which the change in length happens. It's perpendicular to the direction of the strain. So let's look at maybe shear strain and stress first, because that sort of is the opposite situation. That's where now the change in direction, the change or the force is now not sorry, the force in stress and strain is parallel to the change of the direction, but it's perpendicular to the surface area. In this case, in shear stress, we're pushing on the side of our bookcase, and so we're pushing along the direction of the surface area that is involved in our strain. So in this case, the force is now perpendicular, parallel to the surface area. So that's our shear strain. Shear stress. Really should not make those mistakes. So now the shear stress is due to a force parallel to the area that is considered the area A. That will cause a shear strain, which is, if we use the notation here, will be a delta x over L0. So that's the change in delta x because of this force, because of pushing against the side of the bookcase, and of course that will be proportional to L0, because that's just what our strain requires. So that's going to be delta x over L0. And so in shear stress and strain, these are also connected. Now they're connected with S, which is the shear modulus, such that F parallel over A, or shear stress, is S times or shear strain, delta x over L0. So shear stress and strain, in contrast to compressive stress and strain, have the force parallel to the area. In this case, the force is perpendicular to the area. Okay. So one final modulus that we need to introduce is that we need to talk about, in addition to shear stress and strain and compressive and tensile stress and strain, is bulk stress and strain. So bulk stress and strain is what happens when the force is now perpendicular to A, but on the entire volume. So if we look at an example here, now there's the same force working from all directions on the total outside volume of the object. So one of the reasons why this is different to, for example, this scenario, is you could imagine that if you compress the object that it actually gets just a tiny bit wider. And so if you also compress it from the sides, you might get a different result. And you do. That's the bulk modulus. So in this case, we get F over A. And because of what this corresponds to in reality, this is actually the pressure of the surrounding medium. So that's the, you could call this the bulk stress, but really this is what we call the pressure. So for example, air pressure around us, water pressure if you submerge something, oil pressure in hydraulic systems. So it is the pressure of the fluid that is surrounding the object. The bulk strain will now be the change in volume over the original volume. And of course they're connected. So the bulk stress, F perpendicular over A, or the pressure, will be the bulk modulus times delta V over V0. And actually I'm going to put a delta P here, because in many cases we actually always have some kind of pressure, and so the change in volume is happening because of the change in pressure, not because we suddenly add pressure, or because suddenly there is pressure that appears from nowhere. It is because of the change in pressure. This is in contrast to, for example, compressive stress and strain. So in this case, you could actually think of this force not being there. And if there's no force, then you have an original length. But in the case of pressure, we're going to think of this as the change in pressure. So I'm going to write here, pressure change delta P. So that gives us our bulk modulus. And another number that you'll often see used is the inverse of the bulk modulus, 1 over B, and that is the compressibility. And so, just as with the Young's modulus, a large B corresponds with little change in the volume. And of course, if we invert that, a large K corresponds with a large change in V for a given change in volume. So things that have a large compressibility are easy to compress, and so the same force will change their volume significantly. One of the things you'll see in compressibility is that it will often be expressed in per atmosphere, 1 over atmosphere, where atmosphere is one atmosphere is the atmospheric pressure in normal conditions. It's a defined quantity. I think 1016 hectopascals, I think is the definition. In any case, if we have something that is, for example, that has a compressibility of, let's say, 0.1 per atmosphere, then it means that it will change if I increase the pressure by, well, then you can calculate from that, of course, what the change in volume will be, and it's much easier to use this when we're talking about atmospheric pressure changes and pressures that are expressed in atmosphere. Okay, so we've introduced bulk modulus, elastic modulus for compressive and tensile stresses, and we've introduced the shear modulus. One last thing I want to go over, and this is just the last section of this chapter, is that this really only describes the small changes, the small strains and stresses where the behavior of the material is elastic. So essentially where we bounce back without changing the original shape of the object. If we start to introduce larger strains, then we're actually going to permanently deform the object. We're changing its shape, and so you could imagine we're applying a stress, we're still in the elastic regime. If we were to let go of the stress, we go back to the point where there's zero strain. However, if we keep applying more stress, at some point we get into this plastic regime where the object will start to deform more than what we would expect from the elastic modulus. And so if we let it deform a little bit and then remove the stress, then we're actually there's still going to be an elastic slope to this here, but we're going to go back to a different point from where we started. So the object is going to be this much longer even when we remove the stress. If we were to increase the stress even more, then we're going to get, plastic deformation. At some point we're going to get, of course, fracture, or the object will break. In particular, if we do sort of tensile measurements, then it will just break in half. If we do compressive stresses, then the object will likely break by buckling instead of breaking in two pieces. One thing you might have seen is that we do these measurements in sort of tension machines where we put kind of dogleg, or they're called dogleg shaped samples in there, which have a very well defined cross-sectional area here. We clamp them between large hydraulic presses or tension machines, apply a force on either side, and we measure the change in length of this object until, of course, at some point we reach that plastic deformation and then ultimately the fracture point, and then the piece breaks in half. And so we use that kind of technique for characterizing materials, characterizing their elastic region, their elasticity, their Young's modulus, and then when they reach the plastic deformation point and the fracture point. In the case of engineering, of course, we want to remain well in this elastic region. We never want to get into the plastic deformation region for anything, at least, that is supposed to be a permanent structure. When do we want to get into the plastic deformation region? When you build, for example, crumple zones for cars, where you use the plastic deformation to absorb the stress and to absorb the energy that comes with the stress, because now the stress, which is the force, corresponds with a displacement, and we have a large displacement that absorbs a lot of energy because of the stress. So we can absorb the energy through the plastic deformation. In the case of the elastic regime, we're not absorbing energy, or at least when the object moves back to its zero stress situation and zero strain situation, the energy gets released again because it essentially acts like a spring. So this is a very general curve for applicable to many different materials, where we have the elastic regime, the plastic deformation, and then ultimately a fracture point. So the thing that will change between different materials is how steep is this slope. So a steeper slope corresponds to a larger Young's modulus, or a stiffer material, and a shallower slope will correspond to a smaller Young's modulus, because then, of course, we have a large strain or a large elastic deformation for a small force applied. Okay, that's it for today. And so on Wednesday this week, we're going to continue talking about gravitation, and then we'll take it from there. So talk to you all on Wednesday.